Hey everyone, welcome to week 3 management accounting. Today looking at costs further, a fair bit of practical mathematical problems to solve. So without any further fiddling around, let's jump in, see what we can discover today. So we're looking at how costs behave, and we'll be looking at a thing called high-low analysis, and also just looking further at this straight line cost function. We looked last week at fixed costs and variable costs, so we'll see a little more of that, the way they behave, and also how are we going to estimate our cost. And so the quantitative analysis will be using a fair bit of mathematics there, and the financial calculator as well as Excel. We're going to use both of those. We're also going to look further at what is it that's driving the cost of our cost object up. So whatever we're looking at, is it machine hours? Is it labour hours? Is it the number of quality control tests? What is it that causes the cost to drive? And therefore, that's going to help us when we're budgeting and planning for the future. And right towards the end, just looking at some potential data problems that we might incur, such as, what if things aren't standard and we've got this error that occurs, some sort of malfunction somewhere in the production process. Yep, I think that's fairly straightforward. A fair bit of graphing, a fair bit of mathematical calculation, the slope and the y-intercept. So we're applying a little bit of your mathematics from school days, or if you've done business maths and statistics, this will also help you. So there's our straight line formula, made up of, so pretty much the vertical axis will be the y-axis, the horizontal axis, this axis here, the x-axis. So what we would normally be doing is measuring the dollars, total dollars. So this will be dollars here, and the x will be whatever our driver is, whatever our cost driver is. So it could be labor hours, could be machine hours, could be number of units produced, whatever the level of activity is that we think is forcing the cost up. And B is the slope of the line. And so for us, that's going to be the variable cost. So we produce nothing. If X is zero to whatever the slope is, if it's $2 per unit, then obviously this will be zero. And we will find what we'll be left with is the A, the y-intercept. And that is, when X is zero, where do we plot? Where does our line start? We only need 2 points to graph our line, the slope and the y-intercept. So let's keep going, see what we can discover. One way to do it is a couple of buttons for those that are using the financial calculator. If you've been doing business maths and stats, a lot of this you'd be comfortable with anyway, but just quickly recapping, a whole lot of stuff is stored in memory. We need to clear it. So to clear it, it's second function, alpha, and then press the 0 twice, 0, 0. And that will clear all of the memory out. Then we're ready to really we're ready to start entering data. And so the reason I'm laughing is there's a couple of phrases I'm trying to avoid using. I've got used to the idea that I'm filling gaps in, and I'd rather pause and let you think about what I'm talking about. Okay, so a couple of other things we need to do is set up the decimal places. So to do that, we'll press this setup button and just check. We want to run to possibly at least 4 decimal places. So setup, and then we press 0, and that tells us, we press 0 for display. That'll come up on the screen. It'll actually say DSP display, and it'll show 0. So it lets you know, yes, I want to change the display. So you'll press 0, and then it'll come up with tab. And yes, you want to change the settings. So press 0. And finally, it'll give an option of, well, how many decimal places? And if you press 4, you'll get 4. If you press 5, you'll get 5 decimal places, etc. From time to time, you might need to use the scrolling buttons to check how you've entered the data, if you've entered the data correctly. Then we want to make sure we're not in normal mode, but stat mode. So for us, drawing a line A line is two sets of data, the cost driver, the X, and Y, the dollars. So this will be, it won't be one set of data, it's just not the X data, it's X and Y. So we'd go mode 1 for stat mode, and it's asking you now, well, what do you want? 0 for SD, single set of data, or 1 for a line. So you'll go mode 1, 1, and you've got it set up for determining the slope and the y-intercept for a line. We're ready now to enter our X data and our Y data. So we're going to use this XY key for the X set of data. So if, for example, if the labour hours were 45, the first set of data for our labour hours, we'd go 45, press XY, and then it said the dollars corresponding to that 45 labour hours were, say, $900, you'd key in 900 and then press the enter key. The screen will say data set 1, and so you'll know that you've successfully entered the data for that. And then once you've got all of the data sets entered, you're ready then to, you may be interested in finding out what the average labour hours were. So you could go recall 4 will give you the mean of your X series of data, or the average amount spent on your labour dollars or something. So recall 7 will give you the mean of Y. We've also got these population standard deviation over here. So recall 9 would give you that if you wanted to see what the variation in the dollars were, or the variation in labour hours. Recall 6 will give you the population standard deviation. But the main things, there were 4 buttons we'd be interested in. The A, the B, the R, and this predicted value of Y and predicted value of X. So let's have a look at that. So for us to find the intercept, best way to remember for us, that's going to be the fixed cost. So for us, we would go recall division key is going to give us the A, and that, if we've entered the data correctly, that should be the fixed cost component of our total cost curve or total cost line. And then if we go recall delete key, that'll bring up the value of the slope. One way to remember which one's the slope. You're in an exam or something, you think, which is the slope and which is the intercept? I just keep saying B sloping down the hill. I imagine somebody sloping down a hill, B sloping down a hill, and A intercept. I've got A intercept. Bad grammar, but if that helps it, whatever memory jogger you want, that will be the fixed cost and the slope will be the variable cost. More of that in a few moments' time. And then this R is the correlation coefficient. It's really trying to say, what's the relationship like? Is it strong between our X values and our Y values, between our labour hours and our labour dollars? Is there a strong relationship? If there is, we can rely on that. So more about the correlation coefficient in a moment. So to make that happen, it's because it's green, recall open bracket. These 2 other keys here are gold, so we need the second function key to bring them into play. And what they enable us to do, because remember we said we only need 2 points to plot a line, the slope and the y-intercept, the variable cost and the fixed cost, we can then, for any X value, predict what Y might be. We might say, well, once we know that, we could say, well, what would happen? We could predict if it's reliable, and we said, I wonder what the cost would be if we used 56 labour hours. So you could go 56, you've entered the labour hours, and go second function open bracket, and that's going to give you the answer. It's going to plot in, it's going to multiply 56 by the slope and add the y-intercept to give you a value here, the anticipated expected value of y, given you've entered the X. You also could work backwards. You could say, oh, how many labour hours could I get if I was spending $90 or $900 on labour hours? So we would enter $900 and then go second function X, and it will work backwards using the total cost curve, the slope, and the y-intercept to tell us what the anticipated labour hours would be if we happen to spend $900. Again, it's all about how reliable is this R. So more about that in the next few steps. But you've got a choice. You could use the calculator or you could use Excel. So let's see how Excel works. So these are all the buttons we would push. Again, this is just showing you on the calculator what you would do and what it would look like graphically. So another example, simple data, entering a few data sets. Looks like I've forgotten to enter the first data set, which is 0, 0, which means the line, there is no fixed cost in this particular example. When we had 0 unit, let's imagine X is units and Y is dollars. When we had 0 units, there was no fixed cost up here running across the page as we saw last week. So it's totally variable. And it's only the slope which is causing this cost to go up here. So this is like our variable cost curve, if you like, with no fixed cost. So 0, 0, the y-intercept, when x equals 0, y equals 0. So the line starting here. And notice the slope is very easy to predict here. It's just, well, it's the change in y over the change in x. And so it's 200 divided by 100. So it's 2. The slope is 2. When we went up, when x increases by 50, y increases twice that to 100. So if you were to enter all this data correctly, if you went recall A, you should get 0, no fixed cost. If you go recall B, you'll get 2, the slope of the line. And notice that it's got, if you were to go recall open bracket, you would get 1. It's a perfect positive correlation between what's happening in X and what's happening in Y. All the dots are on the same line. There's no deviation from the line whatsoever. Unrealistic in real terms, but for us right now, you can see that's what's happening. In real terms, we would have deviations. We don't have a perfect cost driver in the real world, but here we go. That's what happens. So that's what you'll expect. You'll know if you're hitting the right buttons if you get those results down there. Let's have a look at an example using Excel. So I've got some data here in my C column here, the number of service reports, and I'm thinking that that is the thing that is costing up our customer service department costs. Makes sense. The more that we do, the more reports we do, one would expect our service costs will, increase or decrease in relation to that. So we've captured that data over a set of 8 weeks. So all we need to do is somewhere on our spreadsheet. So I've decided to create a formula here at G9 to help me find the variable cost, the slope. So the formula in Excel, you could click on your function keys and your insert function, and you're looking for the slope formula. But if you hit the FX button, it'll automatically come up with a window to help you write the formula in case you forget. You'll be prompted. It'll say, I want you to enter the Y's and then I want you to enter the X's. But if you hit that FX, the window tells you, it says, whereabouts are your Y values? And so you've just got to highlight down the row of Y's from D29 down to D36. And then it'll say, where's your X values? So you click in where the X's are and highlight. It'll automatically fill in the data for you as you highlight over your X values. That will fill that window for you. And then you press OK. And it's come up with a variable cost of 29. So what that's suggesting is every report we do, every time the number of service reports goes up by 1, the cost, we're expecting the customer service department cost to go up by $29, slope of the variable cost curve. And then if we want to find the fixed cost component in this batch of data, there's another formula called the intercept. And so we type that in or hit insert function, go looking for the intercept function, hit the FX button, which will bring up this window and again tells you where are the Y's, enter your Y values, click on the X, enter the X values, press OK. And it looks like when X is 0, when the number of reports is 0, we've still got some customer service department costs of $8,716 is the estimate for fixed costs. Now, the last one is the correlation coefficient, because we want to know how reliable is that for us to be able to predict, because we've only got 8 weeks worth of data. How could we predict what the cost might be if we run at an activity level of, say, 300 or 200? We should be able to use this formula then to predict within this range of data. So the correlation coefficient, another formula in Excel, instead of, remember on the calculator, it was recall open bracket. For us to enter it, we would type the correl is the Excel formula. Again, tell it where the Y's are, tell it where the X's are, press OK, and it's found a value of 0.80. All the dots aren't on the line. There is some deviation. And what statisticians tend to do is square that R. So by squaring it, 0.8 times 0.8, we get R squared, and it is the, I believe that's the coefficient of determination, and it's, I'll check on that if I've got that wrong, but that 0.64, the statisticians are saying, look, it looks like 64% of the change in these values in the Y values is occurring because of the change in these X values. So the other 36% is due to other factors beyond the number of service reports. So it's reasonably reliable, fairly strong, anything around that 80%. If it gets to 50, it's pretty weak. 40, 30 and gets to 0, we could sort of suggest there doesn't seem to be any correlation. This goes up and this might go down. This goes down and this might go up. So it's all over the place, but it seems to be some sort of realistic trend. Now, when you do business maths and stats, you actually look at the formula to see, well, how is this calculated? It's looking at the Y values and its variation from the mean, and the X value and its variation from the mean, and the relationship between the two multiplied together, the two deviations multiplied. So there's a fair bit of clever mathematics going on there to come up with this figure. And this is what it looks like on the graph. If you were to graph, highlight the data there and insert a line graph, you would get these. A scatter graph particularly would graph all of the dots. So looking at it, you can see all the dots aren't on the line. There is some deviation, but this, theoretically, this linear regression line is the line that minimizes the distance between all of the dots. It's, yes, just looking at it, the line of best fit, you would probably draw a line very similar to that anyway. It's certainly not a line sloping down. It is a line sloping up. The more you use, the greater the cost. So it's sloping this way. And of course, when we take it all the way back to when X equals 0, we're getting that 8,700 mark for the fixed cost. So just revising then, variable cost is going to look like that, fixed cost like that. And if we get a mixed cost, we'll have a fixed cost component with the variable cost layered on top. And essentially that's what your total cost curve looks like, fixed cost plus variable cost. So there's a couple of assumptions we need to be careful about. We really want to make sure, what are we looking at? Make sure that the data we're picking up is relevant to the cost object we're trying to identify. We said last week that could be we're trying to cost out a hospital bed maybe, or we're trying to cost out a particular product, or a particular truck route or airline flight. So whatever we're trying to focus on becomes our cost object. We've got to watch the time horizon too. Costs will vary the longer the period of time. It makes sense that costs will not be held constant. They will be changing. And the relevant range, we can really only predict fixed costs and even variable costs within a certain range of activity. We'll show you how that varies over time. Here we've got an example of maybe where this is from the textbook, we're producing snowboards, and we've graphed the total cost curve, and it looks like the relevant range that we're interested in, we can hold costs constant over this particular range between 20,000 and 70,000, costs seem to be, variable costs seem to be, reasonably constant. With our given level of equipment and activity and everything, it looks like if we go beyond that, there's not going to be enough equipment or room or space to be able to get the job done. So we slow down, and it's costing us more to go beyond this level. And if we're underutilizing our equipment below this level, it looks like people are standing around waiting, with nothing to do during this time. So this seems to be the most efficient range in which we can maintain this level of cost activity. So yes, how are we going to identify costs? We certainly will be looking into the past and to try and predict into the future. And it's going to help us with our budgeting and planning and control. I might move on. It is important that we just find, just because we get a high R value, that R and that R squared that you saw, that correlation coefficient, it doesn't mean that there is a link. If I said to you, I was measuring, I'm looking at some X values and a Y value here, and I'm trying to, I count the number of shoes that people have in their wardrobe, and up here on the Y axis, I also think that there might be a relationship between the number of car accidents that they've had over their driving experience, and so I gather that data. And imagine all the dots lined up beautifully, and I got a correlation coefficient of 0.9. Can I say, wow, I can say with confidence now that 90% of the change in the number of shoes in your wardrobe is affecting the number of, obviously I can't. There's no link. So just because you get a high R value, you really have to use some common sense as well. I think but yep, we've mentioned pretty much everything that is on this slide. So how can we estimate costs? There's a few different methods we'll walk through. We're going to focus on these mathematical methods, but we'll have a look at these three methods first as well. So the industrial engineering method is really, we're going to involve the production people in this, the engineers and those that really know the operation well, get their ideas. It could include time and motion studies, and that's where we could employ somebody independently to capture this, or get the local engineers. And what's interesting is that people on the shop floor, people that are on the production floor, they're pretty smart. If this guy here was to glance across and watch somebody with, a hard hat on or something, and a stopwatch or a laptop and a clipboard, and just watching them carefully, he's going to be a little bit suspicious, and most likely he thinks, I'm being timed. Maybe they're setting a budget. Maybe I'll just slow down a little bit, so that the targets I get will be just that little bit easier to meet in the future, and I'll look good because, or the rest of my team will look good because what they're predicting it, we should be able to achieve this, and we'll be able to meet our targets comfortably without any issues. So we might get some unreliable results just in practice and trying to capture. And these studies are quite expensive. But there it is. It's one method of gathering costs, gathering data. Another method is just get everybody together and have a meeting, shall we? Have a chat about what's going on, get the production people involved, people on the floor, and get everybody to throw their ideas in. And the problem is, it is a bit subjective, and perhaps the person that has the loudest voice gets heard more, and we rely on their expertise, perhaps. Another method is for example, let's imagine we've got the shop floor here, and we've got this fixed cost component of lighting the floor, and then we've got electricity also powering up some of this machinery. If they're not separately metered, we might be able to look at the specifications of the machine and know that it chews through, I don't know, 800 kilowatts an hour or something like that. So we could do some sort of analysis and break the total cost down between the fixed cost component and the variable cost component. That is the fixed cost component, lighting the factory, variable cost component, powering the machinery. So yeah, so it's a method. It's pretty easy to use. A little bit, there could be some errors creeping in and maybe a little bit of subjective judgment there based on the, what the machinery can actually achieve. And finally, the quantitative analysis method. It is objective. We just gather the data from past observations and use that to predict into the future at a given level of activity. So we need to choose what is it that we're trying to measure? What's going to be on the y-axis, the dependent variable, the vertical axis? And it's normally dollars. It's normally cost. Probably 100% of the time, that's what we're trying to measure, the cost, the dollars. For us in management accounting, it is anyway. For a chemist, it may well be, they might be trying to measure the results of a medical, like that they adjust to the medical doses of medicine and see what the results might be in the patient. So it's not necessarily dollars, but for us, it will be dollars. We need to identify what is it that's driving the cost up. Is it labor hours, machine hours, number of units, number of quality control tests? What is it we could use that's the most accurate measure for the change in these dollars? Gather the data once we've got that, and then we can use either the high-low method or regression analysis and then work out whether it's effective. What's the correlation coefficient? Can we rely on it? So let's have a look at how that would happen. Here's a set of data with, we think the cost driver might be machine hours, and we're trying to measure the indirect manufacturing labor costs. We think that the more machine hours we use, the higher will be the labor cost. Sort of makes sense, I guess, that you need more people on the shop floor and you're pushing into overtime perhaps as you work the machines longer or to achieve more hours in a given production shift. So we've come along and we've plotted the points over a range of weeks, it seems. And so in week 8, for example, when we were using this many hours, that the dollars were that. So we plot that point, we plot all the points. Look, it looks like they are gathered. It doesn't look like the dots are all over the place. There seems to be some semblance of order, and it looks like possibly it is sloping up to the right. So my line of best fit that minimizes the distance between the dots is something like that. Number 10 is dragging it down away. Would I ignore number 10? If there was an observation that was way down here, I might say, is that just, did we have was a special occasion? Was there a breakdown or something special happened that caused this one-off result? But all the rest seem to be gathered in this sort of a formation. So pretty reliable. So high-low just grabs the highest level of activity and the lowest level of activity. Only need 2 dots to draw a line. So they picked that and hoped that all the other dots sort of fall in place. And so what we do then is we get the change in dollars between the high level and the low level, and over the change in activity between the high and the low level. More of that when we get some data in a minute. But once we do that, we know that if fixed costs are fixed, the only thing that should cause the dollars to change when the level changes is the variable cost component. So we've found the variable cost by doing this little exercise here. And then we can put it back into either the low level or the high level and work out, because we know the total cost, we know the variable cost, and we know the activity level, the last missing figure then will be the fixed costs will emerge when we plug it all into our total cost line. So if this was our data, we're going to have a look at this set of data in the next few slides. But if we thought direct manufacturing labour hours was the cost driver, then we go looking for the highest level of activity and the lowest level of activity and just pick up whatever the dollars are that are relevant to that level and then analyze it. So more of that down the track, and we'll do some questions in the workshop. But let's have a quick look at regression analysis. Regression analysis, the advantage it has is it looks at all of the observations. High-low is only looking at the highest and the lowest, only two of the dots on the line. So in these next couple of slides, I'll get you to use your judgment just by looking at the curve and looking at the dots. Let's try and work out. We've got manufacturing labor costs we're trying to estimate. And so what we do is we look at what happened as machine hours changed and plotted the dollars. So we've got a different x-axis here. And now we're going to see, well, what about labor hours? What did that look like? So a different cost driver. We're thinking maybe it's direct manufacturing labor hours, which is driving up the indirect manufacturing labor costs. Maybe that's the reason. So we plot all those dots. And then before we do the math, just let your mind, your eyes see if you can pick it. Have a quick look. What you're trying to find is which dots are closer to the line. Is it machine hours here? Are the dots closer to the line here, or is it here? Labor hours. Which one? Because we're going to come up with a different fixed cost and a different variable cost. For me, when I'm looking at that, machine hours, the dots seem a little bit closer than here. The dots seem a little further away, and a little, the further they are from the line, the less reliable it is. Does the line go like this? Does the line go like this? These 8s and 5s are sort of dragging, or is the line more like this? It's a bit less, predictable to try and work out what our linear cost line looks like. So here we were in Excel, we're running with machine hours, we're running with labor hours, we've got these total costs, and we can produce, just like you saw before, we run the slope formula to find the variable cost, we run the intercept formula to run the fixed cost, and then we run the correlation formula to find R. And when we're using machine hours, the dots are, we've got 0.52. It's not that strong, but it's definitely stronger than labor hours. Labor hours, the relationship between labor hours and the dollars, they were a bit all over the place. It's got a very low correlation, 0.412, and R squared is 0.17. Getting back to what we were saying statistically, that's suggesting that the change in dollars here, 17% of the change in these dollars is due to labor hours. There are another, 83% other factors are causing the labor cost to go up. And so there's the formulas. If you wanted to track that down, we'll actually do a couple of these examples when we get together in class. Get used to writing the slope and the intercept, and also using the financial calculator if you wanted to use that. Another refresh of the buttons. And this slide, will spend more time on this later, just how you can enter the data and get the results you're after. So with activity-based costing, another topic we'll be looking at in this unit, it really looks very, very closely at a range of cost drivers and tries to accurately predict what is it that, so we set up these cost pools, and we're able to hopefully accurately predict and allocate costs to our cost object. There are some things that cause our line. There are other linear functions, that deviations from that line, if you like. So practical things like quantity discounts means that we don't have a straight variable cost. If we run at a certain level, we can get a quantity discount and our variable cost will start to, drop. Overtime, when does it kick in? So we've got these step cost functions. So overtime is going to make sure that things aren't really on the line. They will step up to the next level. And also learning curves. People might at the start, and where they're up to, whether they've had a cup of coffee, could make a difference between, the production levels and the heat and the season and a few other things are going to make sure that we've got a lot of variations in the reality of where we're up to, you know, this month versus where we were 6 months ago or 9 months ago or last year. And same with the experience curve. As your people come and go, you're bringing in new skill sets, and you're getting perhaps better at your marketing and distribution. And so, you know, firms get better at what they do as they apply and solve problems over time, hopefully. And these three graphs are just illustrating that. That's the one with the quantity discounts, where the variable cost might start here, but after a certain level, we get a discount and maybe another discount here. So and here's the effect of overtime. We can hold up to 7,500, but maybe we're kicked into a second shift, or overtime kicks in, and then maybe we've got to kick into a third shift if we want to run at this level here. I think that is about it. This is our last slide. Some of the areas we've talked about, some of the issues, the data problems, that we could have extreme values. And should we ignore those extreme values? Are they distorting our ability to predict? And inflation will affect costs. So there's a few other bits and pieces that when we're actually recording the data, maybe there's a slight, you know, just for practical purposes, we can't link up the X data that we're gathering with the dollars that we're gathering. It's just, there's a bit of a mix match there, you know, just purely because of the practicalities, and maybe just it's difficult to gather the data that we need, and maybe the data is not reliable. So we really want to make sure as best we can, our systems, our accounting systems, are good enough to capture and record as much data as possible. So we'll look at more questions in the tutorial. So I'm not sure how long we've been going for. Hopefully it's not too long and you'll get a chance to look through this before next week. So look forward to catching up with you.